Thank you, Nick, for explaining data availability and data availability sampling. I think he already set the stage. I don't need to talk a lot more about data availability sampling and how data availability works. I see a lot of questions were there. Maybe I can add a few different angles to it, but really he did already explain most of the things that should be wanting to talk about with regards to data availability. Any particular thing that we wanted to discuss during this? Okay. So I think a lot of the questions around data availability are about, I would like to classify them into two buckets. I think Nick again did an amazing job into explaining the different aspects of data availability guarantees, but to make them into two buckets, there is a crypto economic aspect and a cryptographic aspect. The crypto economic aspect is what we had relied upon forever. In monolithic designs, what we used to do is we used to say that there is a consensus of the chain. This consensus of the chain decides the canonical ordering. It decides the post route of transaction execution through this canonical ordering, and after that, what is the output of that execution. That is what we used to do in monolithic designs, right? And what the main paradigm of data availability based blockchains they unlock is now we no longer want to ascertain the output of the execution of transactions. We try to delineate the two, and we try to say that, okay, let's forget the execution for a bit. I think one of the first papers was lazy ledger, and again, awesome paper, right? Where the idea is can the ledger be extremely lazy? It can be it can be a garbage dump of all the different transactions, and then on top of it, how can we not assert ordering on the DA layer, but assert execution, only assert ordering on the DA layer, but have nothing to do with the execution, right? And now, can we take that execution results elsewhere, someone else who actually interprets the transactions, and then finally gives out the output of that execution. That is the primitive with which we start the data availability guarantees. In this kind of a world, now let's only talk about the ordering guarantees and the data availability. So let's think about it a bit. We have transactional data. We want to know in what order the transactions appear and what are the transactions, right? So that's all we care about, roughly. If we have a canonical ordering on the transactions and they are available, the output of execution, irrespective of how you execute, as long as there's a deterministic state machine on top, and I think Kautuk likes to talk about state machines a lot. He has here written join the community of state machine builders. So if you have a deterministic state machine on top, the output of that execution is always going to be the same. That is the mental model with which we start, right? With that in mind, let's talk about the transactional ordering and the availability of the data. In that, there are two buckets as I started. There is a crypto economic bucket and there is a cryptographic bucket. If you think about it hard, you will see that the ordering guarantees cannot be given by cryptographic ways. Let's try out a few exercises, right? Let's say that we assume that everything is first come, first serve. First come, first serve looks the most fair, but in a distributed system, it's one of the hardest problems because one of the basic primitives for a first come, first serve in a distributed setting is that of a common clock. A shared clock is okay in a distributed setting if there's a single owner, you trust someone, and so on. The moment you go for a decentralized setup, the common clock becomes a hard problem. Now, without the primitive of a common clock, the first come, first serve completely goes for a toss. There are other problems with first come, first serve. Some people say in the MEV communities, they say that first come, first serve might not be one of the most fair ways of doing things. So there are problems. So if you think about, okay, let's forget first come, first serve, we will take it, let's say, by transaction fees. But even with transactional fees, there is no canonical ordering inside that because we have always seen that the miner of the block can always include transactions of their choice. There is no way I can force someone not to include transactions. On top of that, these network, the network delays make it very hard to ascertain what came first, who had the most priority, and whether I can, front run any of those transactions. And that is why we have seen things like flashbots and a lot of activity in the MEV community who are doing fundamental work in order to make sure that the ordering guarantees are as transparent and as fair as possible. With that in mind, if you take all of these properties together, you will see that it all boils down to crypto economic, because at the end of the day, there has to be a block proposer. In leader-based elections, there has to be a proposer. The proposer or the leader of that particular block, they propose the ordering. Everyone else has to agree that the ordering is somewhat correct in whatever manner. On top of which, they also do what Nick was saying, they also actually have an assertion on the transaction data availability. Because, so what they say is that, yes, not only that the ordering is correct, but also the data for all the transactions are correct. Yes, they need to do it, because otherwise, every validator who votes on a particular block needs to know what is contained in that block. Otherwise, if they vote, it can be something crazy, right, that they don't know of. It can have various side effects which might not be what we want. Hence, if you see the consensus layer of a chain, the consensus engine gives you crypto economic guarantees. This is done. If you rely on the crypto economic guarantees, forget the fraud proofs that he was talking about, forget all the things that can go wrong afterwards, because you rely that everyone checked the ordering. So these guys gave ordering, and they also did transactional DA. This is what you do with monolithic designs in general. But suddenly, we want to have better guarantees of DA. We want to not rely on only the crypto economics. We want to have better guarantees where I do not need to participate in this network in order to know whether fundamentally the data is available or not. With that primitive in mind, we want to now have extremely thin light clients, or light nodes as they call it, right? We call them light clients, they call them light nodes, but the mental model is that, can I have an external entity which has nothing to do with this chain to have a guarantee that this transactional data is available? Mind you that the transactional data is not available by itself, it's always available against an ordering, right? So there is always two buckets, the cryptographic, which we will come to, and I think he has already explained it very, very well, and also the crypto economic, which is what we can rely upon if you do not want to go through all these fraud proofs, validity proofs, and all of them. Does all of this make a little bit sense? Yeah, okay. Now coming to the light client part, I think he explained it pretty well. What we do is we think that how exactly can I make it as hard as possible for this proposer to hide the data? That is the criteria with which we start evaluating data availability blockchains, right? Now, if you think about it, what is the primitive? What is the basic primitive that I can use? So one of the first things that how I used to think about erasure coding was that, let's take a compact disk. Not sure, it looks like the median age here is pretty low, but hopefully you guys have seen compact disks where even with the compact disk having lots of scratches, we still was able to play the media or whatever was inside it, right? So what was done is that it was made in a way where even with a few bits and pieces lost, you could still recover the data. It is all around us. In networks, we already do it. In compact disks, we already do it. We do it in all kinds of places. Like this linear algebra is all around us. But the idea is, one of the main things that we need to think about here is how we can flip that idea. The idea was how can I make it possible to recover the data even if a lot of these bits went missing? What if we flip it and say that how can I make it extremely hard for whoever is publishing to actually censor the data? I want to make it hard for whoever written that CD in order to make it resilient against scratches, right? Because those scratches are the parts it wants to censor. Sorry, I came in late. I don't know whether he already covered all of this, but if not, let's say that I have a piece of data and it contains, let's say, 10 chunks, right? In these 10 chunks, the block proposer wants to censor one chunk, right? So what are the ways and means in which I know that all the 10 chunks have been published? One of the ways, and if you think it very bluntly, might be, yeah, I download the data. That is always possible. That is what is happening on Ethereum today, even EIP, post EIP 4844, right? So even if you have KZG blobs, what is the guarantee that the blob data is actually available? You go and run a full node. Running a full node is one of the best ways to know whether data is available or not. You download it yourself, you check the entire data, you know for a fact that it is there. We want to make it easier because running a full node is no joke, and the moment you make the entry barrier that high, you already have a very high cost of experimentation. The entire idea about rollups, according to me, is actually making the cost of experimentation extremely low so that people can run blockchains of their own choice with all these micro rollups which are application specific and so on, making it extremely easy for us to experiment, to make custom state transition machines, to make custom state structures and so on and so forth, the ways which were all very limiting in general purpose ones. That is one of the fundamental thesis around which at least I like to think about this entire space. Now, in that regard, if you do not want to download the entire data, what is my other option? My other option is, yes, you go ahead and sample randomly. How many do you sample? Is one bound. If you sample the whole, you lose the entire plot. So what you do is, you can only do one. So that will be a probability of this guy getting caught. If you choose randomly one chunk, is 1/10. You can keep doing this, but the more you do, the more probabilistic guarantee that you get. However, the problem is that this block, this particular sample might remain elusive because it's so easy to censor this data. Because it's every time is a independent random coin, right? So you choose once and then you choose another one and then you choose another one. What is the guarantee that I will be in a finite, in let's say 10 random samples for let's say many, like let's say 1,000 chunks? What is the guarantee that I will be able to catch this guy? That's the thought. What you do is, now you take that CD example, what you do is you erasure code this to let's say 20 chunks. And how you do it? You do it in a way where you make 2n chunks where only n is needed to reconstruct this entire data. When you choose only n to reconstruct, then what this means is that even if any 10 chunks out of this becomes available, you are able to entirely reconstruct. Then think about what it needs to be done to censor this data. Now you need to censor 11 chunks out of 20. Anything more, even if you give out a single more chunk, you are able to reconstruct this entire data. That is the power of probability amplification. What you do is you now make the probability greater than half, and now you amplify the probability. This is across in all cryptography. Every probabilistic guarantee that you get, a prime number check, a TLS session, like all around us, like all the guarantees that we get are mostly probabilistic, and probabilistic guarantees don't come in one shot. They come after amplifying the probability over multiple iterations. This is the same thing that we do here. We have 11 chunks out of 20. You keep on doing this, and with this probability, you will know that there was no censoring. This is independent of whatever else happens with a big star. So this is one of the core thesis around which we generate this entire data availability sampling primitive. Now comes, okay, whether the encoding was done correctly. What are the guarantees over the commitment? How can I make fraud proofs smaller? What kind of, can I avoid fraud proofs? Can I go for validity proofs? What are the cost primitives? And I don't think, again, he explained it very, very well, right? So you guys already know it. I don't want to drag this discussion to that. There are, of course, core trade-offs. But if this is clear, I think a lot of the data availability guarantees are clear. So again, I don't know the time limitations and such, but let me know if you want to take a certain direction.
I think we will keep it a little short, but we do have like 2 to 3 minutes left. Then this type of question, you can take questions.
Okay. Okay. So yeah. So this is the overall primitive of data availability. Now it's okay. Let's say that let's take data availability as a primitive because yeah, Celestia guys have done amazing job. Hopefully we can do our part in the coming days. And let's say that you have a data availability primitive, and let's assume that data availability guarantees are there by default. No matter what you do, you have a data availability guarantee. Let's talk about the constructions on top. Enough infrastructure, let's build something cool. What kind of things can you build on top? Now comes the security and the security trade-offs. Now we did talk about a little bit about these trade-offs here, the guarantees here, but on top there is sometimes a lot of these different jargons which are thrown to us, and we kind of get lost in what it means for each one of them. So if you build, let's say, an optimistic rollup on top, what does it mean to have a DA which is set, or suppose the data actually gets lost? What does it mean? And if you think about it, in an optimistic scenario, in an optimistic rollup scenario, if the transactional data is not there, then the proposer can do arbitrary stuff. I am a proposer, I am a sequencer. What I do is I take user transactions, I execute them in whatever order, whatever I want to do. I do not push it to a DA layer. I take that data and I say, like, here is an assertion of the end state. Yes, that is great. I now have an assertion of the end, but how do I know whether that is correct or not? Yes, someone needs to execute it. That's the optimistic guarantee. That not only there is at least one honest guy in this entire network who will take the load of executing it and then generating a fraud proof. But if the data behind the transactions are not available, you have a completely insecure system. That is one of the main reasons why DA is extremely, extremely important for optimistic scenarios. Let's talk about ZK. Sometimes what we do is we take ZK as if it's a magic bullet, right? So you have ZK, which means that you cannot falsify execution. Suddenly your primitive gives you extremely, extremely high cryptographic guarantees, non-forgeable kind of guarantees that your execution was done correctly. And why do I need the transactional data behind it, right? Let's think about it a bit. I don't know how much I can move, so here. Let's think about it a bit. What is a state transition function, right? State machines, what does it do? It says that here is my pre-state, here is my transitions, and here is my post-state, right? As the t-shirt famously says, delta t plus 1 equals to, I'm just looking at that t-shirt and writing it, it's some transition function over sigma t, comma t. This is my transactions, right? This is my pre-state. This is my transition function. This is my post-state, right? This is something that they have given us as a primitive. On this kind of things, if you do not get the t, then what happens is your pre-state is actually not the entire state. ZK proofs are insanely costly if you introduce a huge amount of public inputs. If you put the entire state tree of an entire blockchain as a public input to a state transition function over which you want to generate a ZK proof, it's going to be extremely costly. So how it is done is, you're inside the prover circuit, what is done is that as a private input, the entire transactions and the state machine is given, right? Actually not. I'm again glossing over the details. There are traces here involved and so on. But roughly speaking, the thing is you only give traces over the pre-state and then you generate the post-state. Even with that, your state is somewhere here, which is markalized and so on to generate this pre-state. If I do not give you all the transactions behind, you will have an account which will have exactly the correct balance. No one can tamper with it, but no one, including you, can tamper with it. Because you have a frozen account. You do not have a witness to spend your balance. Every balance spent needs to have a witness. You will not be able to show that I have a path to the pre-state over which I need to spend. And that is why even in the ZK primitive, it is extremely important to know the transactional data. Again, glossing over a lot of details, there are traces involved, there are different kinds of things. Not everyone posts all the transactional data. Like for example, a Polygon ZK AVM does publish all the transactional data, whereas a ZK sync or a Starkware does only publish state deltas. There are differences there. There are guarantees there which we lose and we gain when we do them, but let's not go into it. Roughly speaking, this is exactly why for a roll-up, we need the transactional data availability guarantees. Again, I think I have lost my 2-3 minutes again, but happy to take any question either related to all of which I discussed or beyond.
So I have a question that's a little adjacent to this, right? So what's happening is a lot of rollups are using a settlement layer and a DA layer together, right? And a few are using just a DA, right? So when you have a settlement where there's execution, you can have the fraud proof logic there, right? But how do DA layers think about rollups that are exclusively using the DA layer? If I'm an optimistic rollup, what does security look like in that case?
I think it's a very loaded question. There are two ways to think about it. Again, depending on what do you mean by a settlement layer, right? And again, there has been a lot of discussions about what is it about a rollup, right? Is rollup a bridge? Is rollup a sovereign entity? Is it a collection of nodes? Is it a single sequencer system? Is a rollup defined by the state transition function? What happens if the state transition function changes, right? So a lot of discussions have been done over it, but let me talk about two different classes which I think would help me explain some of your doubts. The first one is, let's say we have a ZK rollup, right? You have a ZK rollup, which means that for any rollup, you need two guarantees. You need a DA guarantee, you need an execution guarantee. These are roughly the two things that any rollup needs. In your DA guarantee, what you do is you run a light client, you do a data availability sampling, you have the data availability guarantee, which is cryptographic for the data availability, ordering you agree on the crypto economics, right? Suppose you have the DA guarantees. What do you need for execution guarantees? Forget settlement as we know it for a moment. You know that these ZK proofs cannot be falsified, no matter who verifies it. Yes, there is a big guy, someone like, let's say, an Ethereum, which also verifies it. Yes, it does it. But you, on your own wallet, on your own machine, already have a ZK proof which takes you 60 milliseconds to verify. Why can't you do it on your own, right? So if you do it on your own, and as long as the DA, the ordering doesn't change, there is a cryptographic guarantee that the execution outcome will also not change. It's a deterministic state transition function. There is a data availability sampling guarantee. The ordering guarantee is the same. So as long as all of that is true, your execution output cannot change. So what you do is you take this and you live with it, right? Suppose that's one. The second is, let's say you do not do all of this. Forget all of this. You only rely on this guy, Ethereum, as a settlement layer. But the guarantees remain the same. Why? Because, remain the same in the terms of you do not self-verify it, but you let someone else verify it. So the consensus of this system verifies that the DA ordering guarantees remain the same, and then it verifies the execution proofs. So the guarantees also depend on how exactly the verification is done. With optimistic guarantees, things change a lot. We already have a prototype we built for the sake of it, I guess, which showed that how to build an optimistic design without a settlement layer. We called it OPEVM. It was built on Polygon Edge. It had an execution system of its own. It has a decentralized sequencer set. It has entirety of the fraud-proof evaluation system built inside the L2 itself. So that is one of the novel contributions which I think was extremely interesting for me to do. So even irrespective of whether it is ETH or say Celestia or Avail or whoever, right? Irrespective of the base layer, we just use the base layer for DA, and then how can these guys all agree whether a fraud has been done or not? There are curious differences there when you go into the grind of it. It all boils down to what is the light client guarantee. What does a light client who is not part of this system, what guarantees can you give to them? For this construction, they can still get a highest level of guarantee because this is a light client, this is extremely light, so you have the highest level of guarantees. For optimistic guarantees, you cannot give very good executional guarantees because the execution needs to be verified by someone, there is a fraud proof on top of it, and if your own layer, your own crypto economic set are also the verifiers of your own security, things get convoluted.
That was where the meat of the question was, that like just purely optimistic constructs over a DLA without a verifier on the settlement, right?
Yeah.
Like the security gets like dubious.
Exactly, it gets convoluted. Again, depends on, then you come down to game theoretic guarantees that you can give there. So you now need to say, okay, what is the stake? How much of it is at stake? What happens in the worst case? Yeah, in the worst case, you give a fraud proof, you verify it, those guys all agree, but what if the 2/3 majority of these guys are also colluding together, right? So those are the kind of guarantees which come up, which is again very interesting, but I think that we still haven't gone past a centralized sequencer, so it's a moot point talking about all of these design decisions. Let's have fully built fraud proofs, which is over an immutable smart contract first, and then we can talk about novel design spaces. Yeah.
You still need for DA and execution, we still need the verification on Ethereum before we can publish the DA, right? Because even if I can verify it independently, then how does the DA know that this is the correct data to publish?
DA doesn't need to know. DA just needs whatever be the execution, whatever be the data that was given for ordering, it doesn't even need to evaluate what the data contains. For example, let me take just two examples, a particular example. Suppose there is transaction 1, transaction 2, and transaction 3, out of which this guy is either malicious or not well-formed. A DA layer will actually allow it to get published. The DA layer only will actually publish transaction 1, transaction 2, transaction 3 in this order and get it published. But now the execution guarantee needs to filter this out. These are based rollup constructions where transactional data is directly published onto the DA layer and then execution is done later. There are other constructions which are dominant today, and this is a Tycho kind of a model. There are dominant all the other rollups that we see today are sequencer based. What this means is that it is not getting published. A sequencer is gatekeeper of what is a well-formed or a correct transaction and what is not. There are other things for example, suppose you use Arbitrum today. Arbitrum was one of the first ones who started with a inbox contract on Ethereum where you could have pushed the data, and from there they used to pick up and go do execution. So if there are still good constructions right now where you can try out this stuff, but roughly speaking, almost no one uses forced transactions. Almost no one has the ability to do arbitrary transactions on top. That is exactly why forced transactions are tough to implement. For example, on a sequence